Okay, I start now. Okay, hello, hello. Um, I think we are. I think we are recording now. Hello again. Welcome to this lecture, and so we'll continue still with the discussion on Tikhonov regularization. Just a little housekeeping. In the chat box, I posted the link to the slides. You should be able to access it as long as with the link. Make sure you download the version now because it's updated with more stuff, and also I want to review what we took up last time. So we are still in Tikhonov regularization, and I just want to have a look at it. So we are, the link is on the chat box. Kindly check. It's there. You need to, wait, I'll just share it again. Wait, here again. There, okay. Okay, so it's over there, okay. I hope you can access it. If there are problems with the access, do let me know, okay. So, right, so again, we focus on the Tikhonov regularization, which is actually this one here. There, okay. And then from that, and then we established that the Tikhonov minimizer from the previous lemma, for each value of the regularization parameter alpha, it has a unique minimizer. So I'll just recap the important parts. Okay, actually in here I provided more details on the uniqueness of the minimizer. So check that out. It only requires tools from inner product spaces. So it's you should be able to follow it. And also we derived a first order optimality equation for the minimizer x sub alpha of the Tikhonov functional. And then in discretization, we've seen that solving the minimizer of the Tikhonov functional, or in other words, doing Tikhonov regularization in the discrete manner amounts to solving a linear system, which is given in this text in red. And then we showed some simulations, and we've seen that we need to fine-tune the regularization parameter so that it can give us an accurate reconstruction. So we need to solve for the minimizer in a stable way, and to do that, we need to set a rule in choosing the regularization parameter alpha, and the most well-studied is the discrepancy principle by Morozov, which takes the parameter alpha as the root of this equation, which tells us that we take the x sub alpha of delta as our approximate solution when the residual at that solution is already close to the given the provided value of the noise level. And then we've shown these preparatory lemmas, and then we stop actually here. So we want to show that the Tikhonov, the mapping from alpha to the Tikhonov minimizer x sub alpha is continuous. So to do that, we started from finding by using the minimizing property of x sub alpha delta. So again, I will just shift from the lecture notes slides to the board. So from there, you can actually see this one. There. And this must be less than the value. But before that, let me just define p sub alpha of x be this one. Okay, so that means the value of the Tikhonov functional at x sub alpha delta, because it's the minimizer, okay, this is the minimizer. This must be less than or equal the value of the Tikhonov functional at any other point, let's say z. So here, by using the minimization property, we let x be equal x sub beta, or rather z. So that is equal to x sub beta minus y delta square plus alpha x sub beta delta square. Note we put alpha here, not beta, because we're using the minimization property of x sub alpha of delta. Now, we consider what happens when we make alpha close to beta. What we want to show actually is that when alpha is close to beta, then the corresponding regularized solutions must also get close to each other. So by regrouping the terms, actually it's very easy to regroup it. We can let the left-hand side to 0, and then just write everything here. There. And then you have this one. I should put here. And then what you do is in this expression on the left-hand side, here we add that on both sides. So that's this one here, this one. Here you add them on both sides of this equation, so you will get the first equation there. So that A times x sub alpha delta minus x beta delta. And this expression will be useful later on. Then you have, and then you group them in this way. There should be minus. So alpha delta, and then plus A times, that's none actually. Oops, that should be, what is it anyway? Oh, alpha actually. Delta minus x sub beta delta. And then you also add this one here on this side, and then you group it with the second group here. There. And then from that, we use some, we simplify the right-hand side with using inner products. So if you wanna, to do it, we can use the fact that for inner product spaces, if you have the square of the p plus q, that's just the square of the norm of p, or rather the square of the norm of p plus q, so that's this one. That's the square of the norm of p plus the square of the norm of q plus 2 times the inner product of p and q. And then on this first group here, this one, then this line, excuse me, you let this one as your p, okay? You let this one as your q, okay? Because if you add these two here, p plus q, you will get this one, okay? That's actually p plus q over there. So if you let that one, delta, that's x alpha delta. And then you can see that p plus q is just this one here. So what you actually need to use here is the version that norm of p squared minus norm of p plus q squared plus norm of q squared equals minus 2 times the inner product of p and q. Okay? And also, on the second group here, in fact, we can rewrite this one as 1 plus 2. It's two groups here. And then, so that's for the first group here. For the second group, it's just the same procedure. So you can just let P equals x beta delta. Q is this one here. Oh, there should be no alpha there. And that will lead you to P plus Q, which is x sub alpha delta. Apply this one, and then you will get the next lines over here. That's the second next equation there. And then by applying that one, and again by properties of the adjoint, so you can actually move this A in the first term here to A star, so that's why you have this one. Okay? And then also you do that on the second group there. So that's actually, just group it, plus alpha times 2. Okay? So that's how it works. Now, if you look at the last term there, if you look at the term in the first inner product on the last line, to simplify that further, we use the optimality condition. And from that's lemma 3.9, because as you can see there, A star times A x beta delta minus y delta is just equal to minus beta times x beta delta. That means you can plug it in there actually. And then, so if you plug it in there, then you will get to something like this one. Let me just shift here. Then let's just do that, okay? Oops, stop, okay. Gosh. So what you have here is that you have this one. Square plus alpha times x alpha delta square, and then you will get something like this one. 2 times beta, that's the last line there. Then you have x alpha delta minus x beta delta minus 2 times alpha times the second term there, alpha delta minus x beta delta. And then you combine both, that will lead you to that term over there. So that's 2 times beta minus alpha times this one. And then by Cauchy-Schwarz inequality, that will just give you this one, 2 times, it will be minus alpha times the norm of x alpha delta minus x beta delta times the norm of x beta delta. And that leads us to a more workable result, and then also noting the fact that we can use the lower bound of this one, which is this one, because they are both non-negative anyway, so therefore we can actually get that last equation over here. And then divide both sides by this one. It becomes 1, and then you will get this expression here. And then further, we can estimate the norm of x beta delta here by using the minimization property of x beta delta. So similar to what we did last time. So, and we can also erase that one by this property of x beta delta. Then we can use t sub beta of x beta delta. It must be less than or equal to the Tikhonov functional with respect to beta at any point z. And to get that inequality, we let z equal 0. So that's why we have a sub x beta delta square plus beta times the norm of x beta delta square, and less than or equal to just the norm of y delta square. And then from that, you can use this bound below by beta times x beta delta, same as what we did here. And then we'll get this expression here. And then we use this bound, we take the square roots both sides, and then we have this more workable result, which we can see here that the norm of x alpha delta minus x beta delta is bounded above by some constant times the difference between alpha and beta. Now, if you let alpha approach beta, then that means the right-hand side goes to 0. Then that means that the regularized solution in terms of alpha must approach the regularized solution of the regular solution in terms of beta. And that shows the continuity of the Tikhonov functional. And then also, so after this, now the thing is we are deriving these preparatory lemmas in order to get to the main result, which is the convergence of Tikhonov regularization under the discrepancy principle. So, and next, we have another preparatory lemma which has some nice intuition to it. So this tells us that for any two positive alpha and beta, where alpha is less than beta, there holds the following inequalities. Where in the first one, it tells us that the norm of the regularized solution in terms of alpha is greater than the norm of the regularized solution in terms of beta. But on the other hand, the residual in terms of the regularization parameter alpha is less than the residual with respect to beta. Now, what does that mean? It's like this. Okay, so suppose you have alpha here and beta. Now, if you think of it, if you plot the norm of the residual x sub, the norm of the x sub alpha delta, then this tells us that the norm of x sub alpha delta beta is greater than this one. So you can think of having it subplot like this. That's the norm of square. So this is for x sub alpha delta the norm of x beta delta. On the other hand, the opposite can be said with their residual. So the residual term looks like this. So something like that. That's the norm of a sub x delta. Well, this one is the norm of x alpha y delta square, and then so on. I have this one over here. Okay. Now this tells us that the norm of x, which serves as the penalty term, decreases as the penalty parameter decreases. That the norm of our regularized solution decreases as we increase our regularization parameter. So that promotes stability. On the other hand, the residual, which relates to the data, increases as we increase our regularization parameter. And that justifies the need of fine-tuning the regularization parameter so that it gives the best compromise between minimizing the penalty term and keeping the residual small. So with that, here's how we prove it. First, from the minimizing property, properties of x sub alpha delta and x beta delta, we have these two equations here. And then, so that's just the same as what we did earlier. So this one is the second equation in terms of beta. First one is in terms of alpha. And then by combining these two equations, it will look like this. So if we can have something like 8 times x sub alpha delta, that's y delta square plus alpha less than or equal that same term there on the first inequality plus beta. But what we'll do here is we use the fact that beta is equal to alpha plus beta minus alpha. Very groundbreaking result. So from that, we plug it, substitute that to alpha in the first inequality, and then we substitute it, and actually, I think I'm wrong. That should be the other way around. Where is I'm looking for? Maybe I'll use this. That should be the other way around. That should be that over there. So that should be alpha equals beta plus alpha minus beta. So that's why you have something like beta times norm of x sub beta delta square plus alpha minus beta times norm of, okay? So that gives the last one, this inequality here. And then by applying the second inequality here, in this group here, you apply the second inequality, that's why we get something like in the slides over here, and that uses the second inequality here, so we just plug it in here, okay? And then, from that one, let me write that one. Square plus, again, that should be, that's beta, of course. Oops, that should be alpha. Okay, and then from that we can go to, and then therefore by simplifying this inequality here, okay, so if you look at the resulting inequality, you can do some manipulation there. And but essentially what you can do is you can cancel this one over here. There. And then you simplify that 1 right there, but wait, I think. Okay, so from that one, you can you can simplify that one, and then use the fact that so you have this one here, okay, and then you have the second one, and then you simplify it. Oops. And then you simplify that further. You must get that inequality over there. So that should be so that's how you should do it. So you can move this on the left hand on the left hand side. Okay, so it's like you have this one. Square minus alpha minus beta times x beta delta square. And then by simplifying that one, that will lead you to this. So that's alpha times alpha minus beta times norm of x beta delta square less than equal to 0, and then factoring that one, this will lead you to this inequality over here. Note that by our choice of alpha and beta, alpha minus beta must be less than 0. So that means we should have the first inequality, because this one is less than 0. Then this must, and then not actually there. So let me write it here. And because this one is negative, so that means that we get the first inequality that is actually this one. Oops, that one over there. Now for the second one, it uses the same procedure. So in fact, we need to use the same results. So from this one, this will imply that you have this one. Am I right? Oh. X alpha delta minus x beta delta must be negative, so that's why you have this one. Now, for the second result, we need the first inequality over there, and it works like this. So just wrong. Okay, and for the second one, we need another result. Oops. Okay, so in the second one, we again need the minimizing property of x sub alpha. So that's a sub x alpha delta minus y delta square. And this must be less than equal the value of the Tikhonov regularization of alpha in terms of the other regularized solution. So that's alpha. Okay, and then by rearranging the terms, this will give us this one. Less than times alpha times x beta delta, the norm square minus x sub alpha delta square. Okay? And previously, x beta, this one, by the first inequality, this must be less than or equal to 0 when alpha is less than beta. So that means, and alpha is positive, so that means this entire right-hand side must be negative. And that gives us the second inequality. Right? So we have that important lemma about the related to the terms in the Tikhonov functional. And now let's go to another lemma, which tells us some nice result, where it tells us that when the norm of y delta is greater than delta, then that function, the mapping, the regular, rather the residual function, which takes the regularization parameter alpha, is strictly increasing. And that result actually makes the discrepancy principle well defined. Note that when you have that condition, this means that the noisy data is not dominated by the noise, and that result there tells us this one. Suppose if this mapping here is strictly increasing, so it looks like this. If it's strictly increasing, then that should mean that we must be able to find a value alpha whose value of the residual is tau times delta. Okay? And that alpha must be and this alpha here is our alpha delta, actually alpha delta ny delta by discrepancy principle. And that tells us that our discrepancy principle is well defined. And to check the proof, we'll prove by contradiction. That means if this is not true, then this function must not be strictly increasing. That means you must be able to find alpha 1 and alpha 2 where they are not equal, but they have the same value of the residual at each of them. So that means this must be true. And again, I'll just go through the proof here. And then by using again the minimizing property of x sub alpha 1, then we have this one. On the left-hand side, this is less than equal to the value of the Tikhonov functional in terms of alpha 1, but in terms of the regularized solution, a sub x sub alpha 2. And by assumption, this residual term here must be equal to the residual term in terms of x sub alpha 1. Okay? And then by simplifying this one, you can cancel this one over here, and you will lead to this one. Okay? alpha 2 delta, okay? However, from the previous result, so that's for 0. But from the previous result in lemma 3.12, then it must follow that that should be actually greater than 1 by greater than equal. From lemma 3.12, then x sub alpha 1 delta must be greater than equal to x sub alpha delta. Okay, that's by lemma 3.12. Therefore, combining these two results, their norms must be equal, and that's okay, and that leads us to this one, which means the regularized solution x sub alpha 1 must also be a minimizer of the Tikhonov functional in terms of alpha 2. So that means x sub alpha 1 delta x sub alpha 2. That means x sub alpha 1 delta is equal to the minimizer of T sub alpha 2. Okay, and that's why we get this result here. And then, from that one, of course, by uniqueness, the regularized solution in terms of alpha 1 and alpha 2 are equal. And then, by the first order optimality equation of the minimizers, we have these two equations over here. So the first one is in terms of x sub alpha 1. The second one is in terms of, both are in terms of x sub alpha 1, but note that they are the same in terms of the different regularization parameters alpha 1 and alpha 2. Combining these two equations, this leads us to this one over here. That's alpha 1, the difference of alpha 1 minus alpha 2 times x sub alpha 1 delta must be equal to 0. Because, of course, alpha 1 minus alpha 2 is non-zero, of course, then this implies that the regularized solution x sub alpha 1 must be equal to 0. And again, by plugging this in one of these equations, if you substitute x sub alpha equals 0, then you must get this one, that a star times y delta must be equal to 0. Okay? And then by applying the applying that result over there, then you must get something like this one. And of course, also by the assumption on y, of course, and then we will get something like this. So that's 0. Since a star y delta is equal to 0, its inner product with any term or any point, let's say x dagger, must also be 0 because this is 0. And then by applying the terms of the inner product, that's just y delta times a x dagger, but that's just y delta inner product with y. Okay, that's because x dagger is the solution. And then by writing y delta plus y minus y delta, something like that. And then we will get that one over there. So that's plus, okay. And from the first equation right there, or for the first term here, that's just y delta square. But again, by Cauchy-Schwarz, then that this must be less than equal, this one is just equal to this one, and then this must be greater than equal the opposite, which is minus the norm of y. Delta times the norm of y minus y delta. Okay, that's by Cauchy's wash. And then by simplifying this one, that will lead you to, or rather by factoring that one, this will lead you to this one. And this one is using the assumption that y minus y delta, then this must be this one. That must be less than equal here. And from the assumption that this one must be positive, then this must be greater than 0. And because you have 0 here, and equals, and then you have greater than 0 here, so that gives the contradiction. And that implies that the discrepancy principle is well defined. Okay, and then I think we are ready for the main results. Yes, finally, we're in the main result, which tells us this one. If the regularization parameter is determined by discrepancy principle with tau greater than 1, then we must have the following result, which tells us that the regularized solution must approach the exact solution, x dagger, or in fact, it must approach the minimum norm solution, x dagger, as your noise level decays to 0. That means as your noise disappears, that means as your noisy data approaches the exact data, then your regularized solutions must approach the exact solution. Okay, now here's a proof of that one. Okay, not if y is equal to 0, but by the definition of the discrepancy principle, not if y is equal to 0, then of course it must follow that x dagger is 0 because we're dealing with the linear system. Then x dagger is equal to 0, so therefore in this case we have y delta must be, the norm of y delta must be less than or equal to delta, and that is related to the instance where the noise, your noisy data is being well dominated by the noise. So in that means this will lead your regularization parameter to blow up, and that means your regular solution will be equal to 0, which is also equal to the resulting exact solution here, x dagger. So if y is equal to 0, then the assertion is trivial. So let's assume that y is non-zero. Okay? Then we have this this nice result. Oops. Let me just do that one. Over here. Oops. Okay, and then we have this result here. And then this means that if you take the norm of y delta, and then of course by writing this one in this way, that's y plus y delta minus y, okay? And then by triangle inequality, the slightly different version, this is greater than equal the norm of y minus the norm of y delta minus y. In case you wonder why that works, that's from this one. A variation of the triangle inequality. And then, of course, this one by definition, by assumption, this is greater than equal to the norm of y minus the noise level. Now, because y is non-zero, since y is non-zero, then, and because in this result we want to let a delta close to 0, then we can actually set this norm of y minus delta to be greater than a multiple of the noise level, let's say tau delta, where delta is sufficiently small. Okay, so we must be able to find tau over there, with tau greater than 1, of course. And then from the discrepancy principle, then this must imply that the regularization parameter alpha delta is finite, and therefore we must be able to find a regularization parameter alpha of delta where the residual with respect to the regularized solution is equal to tau times delta. And then by applying the minimizing property of x sub alpha delta, then we will get something like this one. Let me just there. And a minimizing property of a sub x alpha delta, then we must get something like t sub alpha of x alpha delta is less than or equal to t sub alpha of any point. And let's use x dagger because it's not x sub alpha delta, so it's fine. And it's the useful point that we can use over here. So therefore, by substituting, and then by discrepancy principle, we apply it here, then this means that the delta residual is equal to, that should be alpha delta. Delta, this must be alpha of delta. So that means this is equal to t squared delta squared plus alpha of delta times the norm of x sub delta less than or equal to this one over here. Right. Let me correct that one. Okay, and then that will be equal to this one over here. Note this one here. Ax is just y. So that's just delta squared plus. Okay, and then after that we can simplify that further, because since tau is greater than 1, okay, so this will imply that this one is greater than delta, this thing here is greater than delta squared plus alpha of delta times square. And then can simplify this one. Okay. And then we have the following result there, which tells us that the norm of x sub alpha of delta is bounded above by the norm of x dagger. Now, what does this mean? It means that this sequence of regularized solution is bounded. Okay? And then from analysis, that sequence is bounded. So note we take a sequence for values of data positive. Of course, we consider all the regularized solutions as delta gets close to 0. By taking a subsequence, if necessary, it means that this bounded sequence has a convergent subsequence. And by abuse of notation, you can assume that that sequence, the same sequence with the same notation, weakly converges to some point x hat as delta goes to 0 for some x hat in x. And also by using the boundedness of A, it's also easy to show that the corresponding elements in terms of A, so you have x sub alpha delta. It also follows that A sub, their value when being passed to A must also weakly converge to A x dagger. That's easy to show. And by using the lower semi-continuity of norms in Hilbert spaces as what we've seen, it also follows that delta minus y must weakly converge to A times x dagger minus, let's see, y delta, and then y. Of course, y delta must approach to y. Both, because it must approach strong, so it must approach in the weak sense. So by using the lower semi-continuity of norms, then we have this result. Okay? But from that result, okay, okay. And we know the value of that previous term because alpha of delta is chosen by discrepancy principle, so that's simply inf of tau delta, and that is just 0. Okay? As delta approaches 0, and that means that the norm of ax dagger minus y must be equal to 0. In other words, ax, sorry, that should be, that should be hot over there. Okay. Okay, yeah. Went to advance. So that means A times x hat is y. That means x hat is a solution on the linear system. And also also recall that from our previous discussion, the regularized solutions belong to the range space of A star. And from the previous review that we had on analysis, range of A star is contained to the null space of A, take the orthogonal complement. Okay, and because the null space is closed, and that the same holds to its orthogonal complement and of A perp, then it also follows that the limit point of the regular solutions x dagger must also belong to this orthogonal complement. Okay. However, we know that the minimum norm solution is unique and it belongs to the same space. And that means only one thing. That means the limit of the regularized solutions must actually be the minimum norm solution, X dagger. Or rather, yeah, the limit. So that means the regularized solutions must weakly converge to X dagger, and again by the weak lower semi-continuity of the norms we have in Hilbert space, then we have this one. And that also leads to that one, because if you go back to the previous equation, that the norm of X dagger is equal to the ln inf of the norm of X alpha delta. However, from calculus, of course, this is less than equal to the limit. And also we know that this is actually equal to the norm of X dagger. Okay? And that means that one that we see here, that the limit of the regularized solutions as delta approaches 0, then that must be equal to must be equal to the norm of the X dagger. And note that in this statement here, the convergence is on a weak sense. Okay. Now we want to show that the convergence is also strong. That means in terms of the norm, which is our metric in the Hilbert space, and by an argument involving inner products, we have that one over there, that last equation there, that the square of the norm of X alpha delta is equal to this one over here. Okay, but to show that one, I want to show it, so maybe we can. Okay, maybe I'll just write it here. Okay, and from the previous, by inner products, then that one is just equal to, what did I write there? Equals this one, square. So that's equal to plus 2 times this one. Okay, now how do we get the strong convergence? It's like this. Note this one. From our previous result, this goes to X dagger. And then this one, this inner product, by weak convergence, this converges, the inner product converges to 0 as delta goes to 0. So by canceling, you can cancel this one as delta approaches to 0, and that leaves you to this term over here, which is the term in the middle. And then we get the strong convergence, or convergence in the norm of the regularized solutions to the minimum norm solution, which is delta as delta approaches to 0. And that establishes the convergence. But because in regularization, in particular in Hilbert spaces, aside from convergence, we can also estimate the convergence rate. And that's also very important because it helps us quantify the worst possible error, the worst, not worst, but the best possible error that we can get in applying the Tikhonov regularization. And we will tackle that after a break, maybe like 10 minutes. Yeah.